Let me walk you through applying these principles to a concrete example. Imagine we need to design a file processing pipeline with these requirements. Files must be opened before reading or writing. Files must be written before compression. Files must be compressed before upload. And files must be closed exactly once at the end. Starting with our state diagram, I can identify five distinct states: closed, open, written, compressed, and uploaded. The transitions form a mostly linear pipeline: closed to open, open to written, written to compressed, compressed to uploaded, and uploaded to closed. There's also a shortcut from open directly to closed for files that are opened but never modified. Looking at the transition patterns, there is a linear protocol with a single branch. The fluent interface technique would work well here. It handles linear protocols elegantly, provides excellent IDE support, and doesn't require advanced type system features. Now I'll apply the design heuristics. For model first, code second, I've already drawn the state machine. For hide constructors, I'll provide a file.createPath factory method instead of exposing the constructors. For expose only intended transitions, each interface will have methods that correspond exactly to valid transitions in the state diagram. Here's how the interfaces would look. The closed file interface has only open, returning open file. The open file interface has read, returning open file, write, returning written file, and close, returning closed file. The written file interface is compress, returning compressed file, and close, returning closed file. The compressed file has upload, returning uploaded file, and close, returning closed file. Finally, uploaded file has only close, returning closed file. This design makes several error categories impossible. You can't compress a file that hasn't been written to. You can't upload a file that hasn't been compressed. And you can't forget to close a file because the type system tracks whether you have an unclosed file reference. The implementation would be a single class implementing all five interfaces, with each method performing the appropriate work and returning the appropriate interface view. The state transitions happen through interface casting with no runtime state tracking required. For documentation, I would include the state diagram, explain why compression must follow writing, perhaps for efficiency reasons, describing what happens to uploaded files, and clarify the cleanup behavior of the close operations. This example demonstrates how the design process leads naturally from requirements analysis through state modeling to implementation technique selection. The resulting API prevents entire category of bugs while remaining simple and intuitive to use. The key takeaways are that objects are state machines. Most have valid and invalid call sequences, and these protocols should be explicit rather than hidden in comments or documentation. Compile time checking is better than runtime checking. Catch protocol violations when you write code, not when you run it. Choose the right tool for the job. Match technique complexity to protocol complexity. Use the lightest technique that eliminates the mistakes your users are most likely to make. Now, here's the fundamental change I want you to make. Stop thinking I'll document the protocol and trust developers to follow it. Start thinking how can I make wrong usage impossible to express. When you encode protocols in the type system, you get fewer production bugs because invalid states can't be constructed. You get faster onboarding because ID is guide. new developers to correct usage. You get better code reviews that focus on business logic rather than protocol policing. And you get reduced testing because you don't need to test impossible scenarios. A protocol that exists only in comments is a bug waiting to happen. The type system is your ally in creating reliable software. Use it to make your intent explicit and your mistakes impossible.